All right, welcome back. We have made it to the finish line of our series on register transfers. We've covered everything from the basic latches all the way up to complex bus systems. And today, we're going to tackle the final and maybe the most important piece of the puzzle, the three-state bus and how we use it to talk to memory. Okay, let's get into it. So, if you remember, we've already looked at how a multiplexer-based bus works, right? And it's great at letting a bunch of different registers all send their data to a single destination. You can think of it like a one-way street, where a bunch of side roads all merge onto one big highway. But that brings up a really important question. What if the destination needs to talk back? How do we turn that one-way street into a two-way superhighway for our data?
Well, the problem is really just how a multiplexer is built. At its heart, it's a selector. Its job is to listen to a whole bunch of sources and pick just one of them to pass along to a single destination. It just wasn't designed for data to flow backward.
And you can see it perfectly right here in this diagram. All the data flows from the source registers, it gets funneled through that multiplexer, and then it arrives at the destination. It's a clean system for sure, but it is strictly a one-way trip. So to get that true two-way communication, we're going to need a totally different kind of component.
And that component introduces this really cool concept. A third, almost invisible state that goes way beyond the simple ones and zeros we're always talking about. This right here. This is the secret to unlocking two-way data flow.
So let me introduce you to the three-state buffer. It's a special kind of logic gate. Now, just like any other gate, it can output a logic 1, a high voltage, or a logic 0, which is connected to ground. But it's got this third trick up its sleeve, a high impedance state, which we'll often see called high Z. This slide breaks it down with a perfect analogy. Think of a bus line like a big conference call. When a device is outputting a 1 or a 0, it's actively speaking on the line. But when it enters that high impedance state, it's literally like hitting the mute button. Electrically, it's as if the device has been completely disconnected from the wire. It's not a 1, it's not a 0, it's just silent. And that lets someone else on the line have their turn to speak.
Okay, so we have this magic mute button capability. How do we actually use it to build that two-way data highway we've been talking about? Let's see how it all fits together.
So here's our basic building block. You've got a register, right? But its output doesn't go straight to the bus. No, instead, it passes through one of these three-state buffers first. And there's an enable signal that controls that buffer. When that enable signal is high, the register's data flows right through to the bus. But when the enable is low, the buffer flips into that high impedance state. It goes on mute.
Now, because of this, we can connect a whole bunch of registers to the exact same bus lines. But here is the absolute golden rule. Only one device can have its enable signal active at any single moment. This lets that one specific register speak or write its data onto the bus, while all the other registers are in their high impedance state. They're effectively just listening or reading from that same bus.
So what the three-state bus does is create a shared party line for data. Some control unit decides who gets to talk by turning on just a single enable line. That register writes to the bus, and at the same time, that control unit can tell one or even a bunch of other registers to load whatever data is currently on the bus. So you have one writer and many potential readers, all using the same set of wires. It's just incredibly efficient.
Okay, this is all great in theory, but where does a system like this really shine? Well, let's apply our new bidirectional bus to one of the most fundamental tasks in any computer, reading from and writing to memory. Let's kick things off with a memory read. Now, in what's called Register Transfer Language, or RTL, we write it just like this. And this statement, it tells a pretty simple story. The arrow just means gets the value of. So the data register, or DR, that's our destination, and it's getting data from M, which represents our main memory. But which specific piece of data? Well, the one that's located at the address currently sitting in the address register, or AR. Okay, so let's walk through what actually happens. First, the CPU puts the address it wants to read from into the address register. Then, the memory controller decodes that address to find the exact spot in RAM. And now, the memory unit itself becomes the speaker on the bus. It puts the data from that location onto the shared data lines. Finally, the data register gets a load signal, and it just copies whatever value is sitting on the bus. See? Data flows from memory to the register. All right, that was reading. Now let's flip it around and see how we write to memory. Notice the arrow has changed direction. Now, the memory location that's pointed to by the address register is our destination. It's about to get the value that's currently stored in the data register, DR. The process is pretty similar, but the roles are completely reversed. We put the address we want in AR and the data we want to write in DR. The memory controller finds the right location, but now the data register's three-state buffer is enabled, which makes the DR the speaker putting its contents onto the bus. The memory unit, which is now in listening mode, reads that data from the bus and stores it away. And there you have it. Our two-way street is fully operational.
So now that you've seen how all these pieces work, from the three-state buffer all the way to memory operations, it is time to put that knowledge into practice. It's time to design a system yourself. This is your final challenge for this series. You need to design a complete system with multiple registers and a bidirectional bus. Your system has to be able to perform two specific operations: reading from the address in AR2 and putting it into DR1, and writing the data from DR2 to the memory location stored in AR1. Trust me, this is the perfect way to make sure everything we just covered really sticks.
And just like that, we have reached the end of our deep dive into register transfers. I mean, think about it. We started with the humble latch. We built that up to registers and RTL. We explored bus architectures. And today, we unlocked true bidirectional communication with the three-state bus. You now have a fantastic foundation for understanding and even designing complex digital systems.
I know a lot of you have exams coming up, so really take these concepts, work through that design challenge, and go ace those questions on latches, RTL, and system design. You've got this. Good luck.